Hello. We're going to do an introduction to chemistry today. Um, Let me warn you, introductory chapters are usually not fun, okay? You will hear me say over and over and over, if you listen to my videos, that I don't like memorizing. I don't have a very good memory. I'd rather understand than memorize. But sometimes you need to memorize. You're beginning a new subject. You need to be able to speak the language, right? For instance, if I told you, ¿qué te hace pensar que no tienes que hablar este idioma? You probably didn't understand me because I spoke in Spanish. Shalom, ani begonia. That's Hebrew. Again, you don't understand it. So you need to learn the language of chemistry. That's why this introduction is going to present you a number of terms that you're going to be using later on. If you want to speak to someone who speaks Spanish, who speaks Hebrew, you need to learn the language. If you're going to be dealing with chemistry, you have to learn the language too. Okay? So, what is chemistry? To begin with, chemistry is the study of the composition, properties, and interactions of matter. Okay? And people have been wondering about it for a long time. Think about the old Greeks 2,500 years ago. They thought that matter was composed of basically four elements: earth, air, fire, and water. A few non-scientists wondered if matter was composed of something different, but these were the scientists of the day. Okay, of course we know they're wrong. After the fall of the Roman Empire, there was no science really. We had alchemists that all they were trying to do was transform base metals like iron and lead, we're talking about cheap metals, into noble metals like gold and silver. Of course, it didn't work. But what I'm trying to say is that there was no chemistry for a long, long time, basically until we got into the 1800s. Okay? But we study chemistry because it's so related to so many other sciences. Okay? To give you an example, I began as a biologist. I wanted to be a molecular biologist. Okay? When I was an undergraduate, I got tired of going to my professor asking questions like, okay, so the first NADH forming glycolysis cannot enter the mitochondria. Why? And my professor would look at me and say, don't worry about it. That's chemistry. You know, it seemed like every time I had a question, the answer was, that's chemistry. So when I finally made it to graduate school, I got a degree in chemistry. Then I could go back to biology and say, now I understand, because biology, molecular biology and chemistry, they're very close together. You can ask my students. My biology students complain about, this is supposed to be biology and all you talk about is chemistry. My chemistry students complain, this is chemistry. Why are you giving us examples from biology? Because they're connected. And I want to see that connection. Okay? Chemistry is a science. So it's going to be based on observations, experimentations, and the scientific method is really a systematic way of reasoning. Have you ever tried to do something and you find yourself going around in circles? You keep doing the same thing all over again. You forgot something. I go shopping. If I don't have shopping list, I keep walking around the same place. I know I need something else. I don't remember what it is. The scientific method is nothing more than a systematic method where you cover everything you want to cover. You don't forget anything. You don't waste time with redundant things. So usually you have an observation and you formulate a hypothesis. That's a tentative explanation. But to be a good scientific hypothesis, it has to be testable. That's very, very important. For example, I moved to Greenwood, South Carolina from Clemson, and I had a bunch of orchids, beautiful orchids, bloom several times a year. We move into an apartment in here, my orchids stop blooming. Okay, what is the problem? If I had said that little green men from Mars were affecting my orchids, that would not be a scientific hypothesis because there is no test for little green men from Mars, right? So I had to come up with real hypothesis. Maybe it's the amount of light, maybe it's the amount of water, maybe it's the temperature. Okay? So being testable is crucial to have any scientific hypothesis. Another thing you need to know is what is a law. A law in science is a summary of a vast number of observations. It doesn't try to explain. It just says, this is what we've seen. Okay? And you use them to describe or to predict something. For instance, if you let go of your pen, what's going to happen? It's going to fall, right? How do you know that? Because in your experience, every time you let go of something, it falls. And that's what humans have observed since they've been humans on Earth. You don't expect all of a sudden your pen to float up to the ceiling. Okay? But it's based, like I say, on a tremendous number of observations. On the other hand, a theory is more of an explanation that is testable. So if I want to know why did my pen fall, then I'll talk to you about it. I'll talk about gravity. And I'll try to explain what gravity is, what causes gravity. But keep one thing in mind, because it's testable, there is always the possibility of an experiment that shows that your theory was wrong. So theories usually vary. Okay? May vary. I'm not going to say. In subsequent chapters, we are going to be talking about atoms, and we are going to see how the theories about how the atom keep changing. They come up with a theory, then someone does an experiment, that doesn't match the theory. So you revise the theory. On the other hand, laws are unchangeable. You cannot violate scientific laws. Okay? I just had to put this cartoon. This person is guilty of breaking the law of gravity. It doesn't happen. It's a cartoon, obviously. How does the scientific method work? Well, you begin with an observation. For instance, I come home, click on the switch, and the light does not come on. So the first thing is wondering, what happened? What is the explanation? And my first suggestion is the light bulb. Okay? The light bulb stopped working. So you form a hypothesis. Remember, we say hypothesis has to be testable. Well, that's very easy. Get another light bulb and replace it, and let's see if the light comes on or not. So you test, you perform experiments to test your hypothesis. Sometimes the test says, yes, you're right. So you was right, your hypothesis was right. In the case of science, you just contributed to the knowledge. But keep in mind, sometimes tests tell you, no, that's not the hypothesis. That's not the reason. You replace the light bulb and still there's no light. So you have to come up with another hypothesis. Oh, maybe I need to check the switch box. Maybe it has tripped. And, well, that doesn't work either. Well, eventually I'll call an electrician. But you do come up with testable hypotheses, you try them, and either they tell you your hypothesis was right or they tell you your hypothesis was wrong. Either way, eventually in science you come up with theories and laws. But it's really neat system because, again, it allows you to orderly set up your experiments where you don't miss anything, you don't replicate what you have already done. We talk about matter, but we didn't define matter. Matter is anything that occupies a space and has mass. Okay? Some people say, well, air is not matter. Yes, air occupies a space. How much? Depends what you're putting, the amount of air. It has mass, it weighs, may not weigh a whole lot. And everybody's familiar with the three most common states or phases of matter. And say most common because we are going to see that there's actually a fourth one. But everybody knows about solid, liquid, and gas. How do we tell them apart? A solid is rigid. Look at the example there. Has the shape of a cube. It's going to remain like a cube unless you do something. Has a definite shape. A liquid, it flows. It takes the shape of a container, but it has a constant volume. I wish this book could. So if you have a quart of water, you can have it in a pitcher, you can have it in a vase, you can throw it on the floor. It's still a quart of water, but it takes different shapes. A gas takes both the shape and the volume from the container, meaning that if you have a bigger container, the gas expands more. I remember years ago, I was teaching in the high school class, and one student tested a pepper spray in the back of the room. It didn't take very long before everybody's coughing, sneezing. We have to vacuum the room because the little bit of gas spread out to fill the whole room. But like I said, just because these are the phases of the matter you're familiar with, doesn't mean they're the only ones. We have one more, plasma. Plasma is a gaseous state, but instead of containing atoms or molecules, it contains electrically charged particles. Okay? We're not going to be dealing too much, at least in this course, with plasma, but you need to be aware of that. It has unique properties. It's a gas in a way, but because of the electrically charged particles, that's going to change some of the properties. And you can find it naturally in stars, in lightning, and now, of course, we have television screens that are made up of plasma. Okay? Very, very easy to confuse, mass and weight. In regular English, we use them interchangeably, but they're different. Mass tells you the amount of matter in an object. Weight refers to the force that gravity exerts of an object. So if I ask you, how much do you weigh? What I'm really asking you is, how strongly is gravity pulling on you? But you're going to tell me I weigh so many pounds. But pounds is a unit of mass. That's what I said in regular, everyday talking. We talk as if mass and weight were the same thing, but they're not. Okay? Do you know an easy way to lose weight? Quick. Move to Colorado. I am in South Carolina, maybe about 100 feet above sea level. If I move to Colorado, I calculate one day I'll lose about 2 pounds. Why? Because Colorado is high and the force of gravity is a little bit weaker. Does it mean I have changed? No. I'm exactly the same person. My clothes are going to fit just as well or just as bad as they did in South Carolina. My mass has not changed. My weight has changed because the gravity has changed. A good example, everyone's familiar how on the moon you weigh less because of the lower gravity. Law of conservation of matter, very simple, but this is something that you need to keep in mind. It's one of those things that will trip you sometimes doing programs. Whenever you have a chemical reaction or a physical change, there is no detectable change in the total amount of matter. For instance, you're going to brew your own beer. Okay? So you put your hops, water, put sugar, whatever, make sure you cap it. And you let it ferment. When it ferments, the glucose is going to make alcohol. That's the whole point of brewing beer, right? And it's going to make carbon dioxide, that's gas. That's why I said, as long as you cap it and you don't have any loss of carbon dioxide, if you add the masses of everything you put in the boil before and everything that's in the boil afterwards, the mass did not change. So what's an element? An element is a type of pure substance that cannot be broken down into simpler substances by chemical changes. If you have oxygen, you can have oxygen gas, you can have oxygen atoms. But if you break down the oxygen atom, it's not oxygen anymore. Okay? So the non-elements, and in this case they're talking about atoms, they're found in the periodic table. Actually, there's 108, I believe. Let me check. I don't know what I'll do with that. My periodic table. 118, sorry. That's what I need to check. In the periodic table. Okay? About 9 of those occur naturally. The other ones have been created in the laboratories, but they're all elements. When you have a sample of anything, you can have a pure substance or you can have a mixture. We're going to see mixtures in the next one. So what is a pure substance? It's something that has a constant composition. Okay? So if I have a tank of oxygen, it's going to be oxygen all the time. If I have a glass of water, it's always going to be water. Now, pure substances can be elements or can be compounds. We define elements as substances that cannot be broken down. They're made up of one type of atom. So say if you have gold, you have phosphorus, if you have oxygen, notice that all of these are atoms. Okay? We are going to see that some molecules can be elements too. But when you have gold, you only have gold. There's nothing else. So that's an element. A compound is a pure substance that can be broken down to elements. For instance, water was made up of hydrogen and oxygen. Sugar is made up of carbon, hydrogen, and oxygen. Silver chloride is made up of silver and chlorine. And very important, the properties of a compound are different from the properties of the elements that make the compound. Let me give you an example. You can have hydrogen. Okay, and hydrogen is a gas and it's flammable. Okay, and I'm going to make it react with oxygen. You know, oxygen is a gas, it's flammable too. When they react, form water. Water is not a gas, it's liquid, and it's non-flammable. In fact, water is used to quench flames. So the properties of the two elements that I began with change. They change from gas to liquid, from flammable to non-flammable, when they combine together. A mixture, on the other hand, is composed of two or more types of matter. They can be present in different amounts, and the important thing, they can be separated by physical changes. And I put a comment in there, evaporation is an example of a physical change because of the example I usually use to show you mixtures. But there's two types of mixtures, homogeneous, heterogeneous. Homo means the same. So a homogeneous mixture has a uniform composition and visually appears the same throughout. Almost like when you're making cookies and you blend the sugar and the butter, eventually you don't see the sugar anymore. That has formed a homogeneous mixture. Some people call them solutions. Although solution usually implies that one of them, one of the components has to be liquid. Heterogeneous mixture, hetero means different, means that you can tell the different components. So this is my example. Imagine you have a glass of water. Okay? So this is water. I'm going to add some sun. Sun is not going to dissolve. And I'm going to use some salt, table salt. And when you stir it, the salt disappears. So the salt dissolved in water is an example of homogeneous mixture because you cannot see it. You cannot see the salt. It cannot disappear when you dissolve it, right? But it's still a mixture. It can be separated by a physical change. If you evaporate the water, the salt gets left behind. Listen, in southern Spain, there's lots of Roman ruins. One of my favorites looked like a giant pool. I'm talking about maybe an acre surface, but it would be only less than a foot deep. And the guide explained to us that those pools were filled with water from the Mediterranean, they were left exposed to the sun, and eventually the water evaporated because it was filled from the sea. It left the salt behind. That's how Romans got the salt. On the other hand, the sun in the world, you can see the sun. You can stare until you get tired of it. So you can always see the sun. So sun in world is a heterogeneous mixture. And you say, well, how do you separate them? You could evaporate the water if you wanted. You can just strain it. That's another physical change. You can separate the water and the sun very, very easily. So this is a summary. I'm not going to go through it because you can read, but it summarizes the difference between a pure substance and a mixture, the different kinds of mixtures, the element versus the compound. So this is just a summary of everything we talk about. I left it in there for your use. We did talk about atoms earlier, and we said that's the smallest particle of an element that still has the properties of that element. And atoms can combine chemically with one another. It was first proposed by philosophers. Remember we said the Greek scientists said that matter was composed of fire, water, right? But some philosophers said, I think that this is wrong. I think there must be some very small particles that make everything, and they used the word atom for it, the Greek word from that. But then it was forgotten. It wasn't until the 19th century when John Dalton decided to prove that that hypothesis was right, and that will be the topic for another video. Okay? When atoms combine, two or more atoms combine together by forces that we know as chemical bonds, they form a molecule. So you can have hydrogen, you can have oxygen, these are atoms. When they combine in the right ratio, you form a molecule. Well, here you have examples of molecules. But I want you to notice something. They all are molecules because they're made up of different atoms. Every atom is represented by a ball. But notice that there's actually two groups. To the left of this line, every molecule is made up of atoms that are identical. So even though they're molecules, they're also elements. So a better definition of an element is matter that's composed of atoms of the same element or identical atoms, where you have one or a million. If you only have one type of atom that are identical, you have an element. Notice that hydrogen and oxygen, you have two atoms in each one. Phosphorus, the molecule is made up of four atoms. Sulfur, the most common form, there's several forms, but the most common form has 8 atoms. On the other hand, to the right of the line, these molecules are composed of at least 2 different atoms. Okay, you see the water has hydrogen and oxygen. Carbon dioxide has carbon and oxygen. Glucose, sugar, has carbon, oxygen, hydrogen. We call this compounds. So this is, but they all are molecules. And I know this is something that tends to confuse the students. So an element can be an atom, an element can be a molecule, as long as all of the atoms are the same. But the compound is always a molecule. Okay? We're almost at the end of the chapter. We're going to distinguish physical and chemical properties because many times we need to figure properties to identify particular substance. We do that in the lab all the time. It's lots of fun. I like those labs where you have to identify an unknown. Physical properties refer to characteristics that have nothing to do with the composition of your molecule. If I tell you that the melting point, or sorry, the boiling point of water is 100 degrees Celsius, it doesn't change water. You can do it in the lab. You boil water, stick a thermometer, read 100 degrees Celsius. The water didn't change, it's still water. We do in the lab determine, for instance, the density of water. And we see different ways that you can determine the density. It doesn't matter, the water remains water. So a physical change is a change in physical properties that without a change in the chemical composition. So if you melt wax where you have solid or liquid, it's still wax. When you dissolve sugar where you have solid sugar or a solution of sugar, it's still sugar. When you boil water, you can have liquid water, you can have steam, but still water. Okay, so that's physical properties and physical changes. But sometimes your molecules change. So the change of one type of matter into another one, or the inability to change, is a chemical property. For instance, flammability. We talk about oxygen and hydrogen were very flammable. Water is not. You can burn easily oxygen and hydrogen. You don't burn water. I'm very bad cooking, but I don't burn water. Okay? Same thing, acidity, toxicity. What is the acidity? Well, it's a chemical reaction in which a particular molecule gives off product. We'll learn all of that. But anytime there's a chemical reaction, there's a change in the chemical properties or chemical nature. You have a chemical property, and a change in the chemical properties is called chemical change. The property is different before and after the change. What happens when you burn wood? Well, you begin with wood, and if you do a good job, you're going to see some steam coming out as part of the smoke, and there's going to be ashes, and there's no wood left. Right? When you cook food, you're changing it from something that may be very difficult for you to digest to something that's easy to digest. You change the chemical properties. So that's a chemical change. The last thing we're going to cover here are extensive and intensive properties. Basically, an extensive property depends on the amount of matter present. Let me give you an example. You can go to the store and you can buy a gallon of milk, or you can buy a pint. Which one is heaviest when you're carrying your groceries to the car? The gallon. Why? Because it has more milk. So mass or weight are extensive properties because it depends on how much matter you have. Intensive properties, on the other hand, don't depend on the amount of matter present. If you're going to measure the density of water, it doesn't matter whether you have just a couple of ounces of water, or you have a whole pitcher of water, or maybe you have a water tank. The density of the water is always going to be 1.00 grams per cubic centimeter at room temperature, and it doesn't change. So that's the difference between extensive and intensive properties. Occasionally, when we are studying something, we tell you, oh, by the way, and this is an intensive property. And you need to remember that, because when you talk about extensive properties, you're going to have to keep into consideration the amount of matter. If it's an intensive property, you don't. So that will become very important, especially when we talk about thermochemistry and all of that. So if you like to work with me on a one-on-one basis, if you want to do practice problems, I have developed a number of worksheets for my students that I'll be glad to share with you. If you're studying for an exam, go to the video description and there will be a link to my Wyzant profile, and you can make an appointment, and I'll be glad to help you.